Stealth is back, and the world is watching. Recently, news about the US reactivating its legendary F-117 Nighthawk has fueled speculation that a next-generation stealth platform, possibly the Darkstar, is in testing. Russia and China, both racing to advance their own stealth capabilities, are on high alert. The return of the Nighthawk isn't just about nostalgia, it signals America's continued dominance in stealth warfare. Is the Nighthawk truly back? If yes, why bring it back now? Join us as we explore the capabilities of the United States F-117, which has terrified Russia and China. Two F-117 Nighthawks flew low over Baghdad, staying beneath the clouds to avoid detection. On the ground, radar-guided missile systems scanned the sky, searching for enemy aircraft. But the stealth jets barely registered, appearing as nothing more than faint blips that blended into background noise. Their mission was clear: strike a high-value target without being seen. As the bomb bay doors opened, two GPS-guided bombs dropped toward a suspected hideout of Iraqi President Saddam Hussein. But opening the bay doors could expose the aircraft to enemy radar. With their position potentially compromised, the pilots quickly turned and exited hostile airspace before the enemy could react. The F-117 was built for precision strikes, not dogfights. It had no defensive weapons and was slower than most fighter jets. Its survival depended entirely on its ability to remain undetected. During the Gulf War, the F-117 successfully struck 1,600 high-value targets without a single aircraft lost. The F-117's development was a gamble on radical technology. Engineers at Lockheed's Skunk Works designed an unconventional aircraft based on stealth rather than aerodynamics. Its sharp-angled, faceted shape, called the hopeless diamond, was meant to scatter radar waves, making it nearly invisible. But experts doubted it could fly. Even Kelly Johnson, the legendary Skunk Works leader, was skeptical. Despite the doubts, Ben Rich and his team refined the design. Using a translated Russian scientific paper on radar reflections, they calculated the ideal shape for avoiding detection. Engineers made precise adjustments to ensure the aircraft could fly while maintaining its stealth properties. The result was the world's first operational stealth fighter, a plane that could strike deep into enemy territory without being seen. Military technology is a constant battle of adaptation. Before stealth, high-speed jets dominated air combat. But as radar and missile technology improved, traditional aircraft became easier to track and destroy. The F-117 changed the equation. Instead of speed or firepower, it relied on invisibility. It wasn't designed to win in a direct fight. It was built to strike before the enemy even knew it was there. From the Gulf War to Kosovo, the F-117 proved that stealth was the future of warfare. Though it was eventually retired and replaced by more advanced aircraft like the F-22 Raptor and F-35 Lightning II, its impact remains. The Nighthawk didn't just change how wars were fought, it reshaped the future of military aviation. In 1973, something shocking happened in the Yom Kippur War, a wake-up call that the US never saw coming. Israeli pilots, flying some of the best American-made fighter jets, suddenly found themselves dropping out of the sky at an alarming rate. In just 18 days, 109 aircraft were lost. But these weren't just dogfights between jets. Most of the planes were blown out of the air by Soviet-made surface-to-air missiles supplied to Egypt and Syria. These Soviet missile systems were a game-changer. Unlike fighter pilots, who needed years of training, SAM crews could be trained quickly and operate at a fraction of the cost. The missiles were devastatingly effective, and the sheer numbers made them nearly impossible to dodge. The Soviets had spent billions developing radar-guided missiles, and their power was terrifying. Take the SA-5 missile, for example. It could soar to 125,000 feet. That's higher than most planes could ever fly and even carry a nuclear warhead. Imagine an American bomber flying into enemy airspace, only to be met with a missile that explodes with the force of a nuclear blast. Even worse, if these warheads were used, the shock waves wouldn't even reach the ground. Instead, the wind would carry the radioactive fallout straight into Western Europe. This wasn't just theory. The battlefield had changed overnight. Military planners did the math, and the results were horrifying. If a full-scale war broke out between the US and the Soviet Union, the entire US Air Force could be wiped out in just 17 days. The Cold War balance had suddenly tipped in favor of the Soviets. Faced with total air dominance by Soviet missiles, US military planners scrambled to find a solution. Two major strategies emerged. The first was to fly as low as possible, hugging the terrain to stay hidden from the radar. If radar couldn't detect a plane flying just above the ground, pilots could avoid missiles altogether. This thinking led to the creation of the B-1 Lancer, a bomber designed to fly at extremely low altitudes. Its swing-wing design lets it fly slow and steady near the ground, but also speed up and climb high when needed. While low-altitude flight was promising, another idea was about to change aviation forever. Enter Dennis Overholzer, a scientist at Lockheed's top-secret Skunk Works division. He dropped a thick stack of papers on the desk of Ben Rich, his boss, and inside that document was something extraordinary, a formula that could predict how radar waves bounce off different shapes. With a hopeless diamond as a foundation, Skunk Works engineers faced a massive challenge, turning a radar-evading shape into a real aircraft. Stealth was the priority, but the planes still had to fly, carry weapons, and complete missions. Every decision had to balance invisibility with functionality. First, the mission profile was set. The F-117 wouldn't be a dogfighter or a high-speed interceptor. It would be a precision bomber designed to sneak past enemy defenses and strike high-value targets with pinpoint accuracy. To remain undetectable, it couldn't carry external weapons. Instead, it would house its bombs inside two internal bays, hiding them from radar. This design limited its payload capacity, but stealth mattered more than firepower. One major problem? The F-117's unique shape made it aerodynamically unstable. Traditional planes have smooth, curved surfaces that help them glide through the air efficiently. The F-117, on the other hand, had sharp angles and flat panels designed to scatter radar waves. This made flying it incredibly difficult. It simply wasn't built to stay in the air on its own. The solution? Fly-by-wire technology. Instead of relying on a pilot's instincts alone, the F-117 had an advanced computer system that made constant adjustments to keep the plane stable. Without this system, the aircraft would be nearly impossible to control. The Nighthawk's engines had to be hidden to reduce its infrared signature, making it harder for heat-seeking missiles to lock on. Engineers buried the engines deep inside the fuselage and used special exhaust vents to cool the hot air before it left the plane. This design reduced heat emissions and limited speed. The F-117 wasn't fast like a fighter jet. It had to rely entirely on stealth, avoiding enemy threats rather than outrunning them. Another trade-off was maneuverability. The F-117 wasn't built for sharp turns or aerial dogfights. It didn't have afterburners, and its unusual shape made high-speed combat nearly impossible. But these sacrifices were worth it. The plane could enter enemy airspace, drop precision bombs, and escape without being detected. After years of secret development, the F-117 was finally ready for real-world missions. It made its combat debut in 1989 during Operation Just Cause in Panama. But its true moment of glory came in 1991 during the Gulf War. The Nighthawk led the first wave of airstrikes, slipping past Iraq's powerful air defenses and destroying key targets with laser-guided bombs. Despite flying deep into enemy territory, not a single F-117 was shot down. It proved that stealth technology could change the rules of warfare. You couldn't shoot what you couldn't see. The success of the F-117 paved the way for modern stealth aircraft like the F-22 Raptor and F-35 Lightning II. Though officially retired in 2008, the Nighthawk's legacy lives on. And now, with reports of it flying again, the question remains, is the US testing something even more advanced? The F-117's main weapon was laser-guided bombs. Inside the nose, it had a moving turret with an infrared sensor that could zoom in and out. A second infrared sensor sat next to the front landing gear. Both sensors had lasers that could lock onto a target and guide bombs with extreme accuracy. The sensors worked with the plane's internal navigation system, switching between forward and downward views to track targets as the aircraft flew over them. However, these systems relied heavily on clear weather. Clouds could block the laser guidance. To solve this, the F-117 could also use GPS-guided bombs. Despite its advanced targeting system, the F-117 had no defensive weapons. It was completely unarmed against enemy aircraft, relying only on stealth to avoid detection. Because of this, it was designed as a subsonic plane, meaning it stayed below the speed of sound. A sonic boom would give away its position, not to radar, but to anyone nearby. Moving at high speeds also caused more friction, heating up the plane's surface, which could make it easier to detect with infrared-guided missiles. To keep the aircraft hidden, engineers chose not to use afterburners or complex engine inlets. Instead, they equipped it with General Electric J85 engines for the early test version and later upgraded to the F-404 engine from the F-A-18 Hornet. These engines were cost-effective, reliable, and easy to maintain. The engine air inlets were another unique feature. Normally, radar waves can bounce around inside an inlet, similar to how sound echoes inside a cave. The F-117's inlets were covered with a special radar reflecting grid to prevent this. This grid had tiny gaps, each just 1.5 centimeters wide. These gaps were small enough to block most radar waves from passing through. Any waves that did get through would hit radar-absorbing material inside the inlet, reducing the plane's radar signature. The entire aircraft was coated in RAM to absorb enemy radar signals. However, covering the inlets created a major challenge. It reduced the air pressure going into the engine. Normally, an engine inlet is designed to maximize airflow and maintain high pressure for peak performance. The mesh covering the F-117's inlets blocked some of that airflow, which reduced engine power. To fix this, engineers added secondary air intake doors that could open at lower power settings to increase airflow. These doors opened automatically when the plane flew below Mach 0.5 and gradually closed as it picked up speed. They also served as an access point for maintenance since the main intakes were covered. Another big issue was ice buildup. Aircraft flying at high altitudes can collect ice, which can block sensors and reduce performance. Small parts, like airspeed sensors, usually have built-in heaters and drains to prevent this. But the F-117's inlet grid was too large for standard heating elements. Instead, engineers installed an anti-icing system that sprayed a glycol-based de-icing fluid. A small wiper extended from below the inlet to spread the fluid and keep the grid clear, ensuring the engines got enough airflow. The next step was shaping the engine's exhaust outlet. The F-117 had a very unusual design because engineers wanted to reduce both its heat and radar signatures. To do this, they needed to cool the exhaust quickly and spread it out over a larger area to blend with the outside air faster. Instead of a simple round exhaust, the design transitioned into a long, flat rectangular shape with a 17:1 ratio. To further control the heat, the outlet was split into smaller channels. Below the exhaust, the fuselage extended outward at a slight upward angle, forming what was called the platypus tail. This special design spreads out the hot air, allowing it to mix with cooler air more effectively. On top of that, the extension was lined with heat-absorbing ceramic tiles that were constantly cooled by bypass air flowing around the engine. However, this unique exhaust system led to unexpected instability during the half-blue test flights. The thrust from the engines was directed slightly inward toward the plane's center line, but this angle wasn't always perfectly balanced. Depending on speed, engine power, and angle of attack, the thrust angles could differ by as much as 8 degrees, pushing the plane sideways. One major issue was something called side slip. This happens when the wind hitting the aircraft doesn't match the direction it's moving, something common during takeoff and landing, especially in crosswinds. The F-117's flight computer used an accelerometer to measure side slip, but the uneven thrust from the engines made the aircraft drift slightly. The computer thought this was a real side slip and tried to correct it, but in doing so, it actually created real side slip, making the situation worse. This started a feedback loop where the plane kept overcorrecting itself. To fix this, engineers introduced a more reliable way to measure side slip using a beta vane, a small device that detects airflow direction. In aviation, beta is the technical term for side slip, and this new system helped the flight computer make accurate adjustments. With the engine and exhaust system set, the next challenge was designing the wings. Engineers had to consider many factors, such as the wing's angle, shape, and size. Normally, designers can adjust these elements based on what the plane is meant to do. For example, an airliner's wings are designed for fuel efficiency at cruising altitude, while a fighter jet like the F-16 focuses on agility and high-speed turns. But the F-117's engineers had limited options. One of the biggest restrictions was the wing's sweep angle, which refers to how far back the wings are angled. This angle is usually determined by the aircraft's speed. Small planes like Cessnas don't need swept-back wings because they fly at slow speeds. Airliners, on the other hand, have angled wings to reduce drag and fly faster before running into issues with shock waves caused by near-supersonic speeds. For the F-117, stealth was the top priority, meaning its wing shape had to fit into the overall stealth design rather than be optimized for performance like a traditional fighter jet. The Boeing 787 has wings that sweep back at an angle of 32 degrees. Supersonic jets, like fighter planes, also have swept-back wings, but their angles depend on speed. The reason is to prevent shock waves from hitting the wings, which would create too much drag and reduce lift. For example, the F-16 has a sweep angle of 40 degrees, while even the super-fast SR-71 Blackbird only has a 53-degree sweep. The experimental HAB-Blue aircraft had an extreme sweep of 72 degrees. The F-117 Nighthawk, however, wasn't designed for speed. It was supposed to fly at subsonic speeds, similar to a passenger jet, so that a 32-degree sweep would have been enough. But the F-117 needed to be invisible to radar, and stealth design forced engineers to push the wing sweep far beyond normal limits. This choice led to some tough challenges. Swept wings naturally generate less lift than straight wings of the same size. The problem was worsened because the F-117's wings couldn't have smooth curved airfoils. Instead, its wings were built from flat faceted surfaces, made of 2 or 3 flat panels on top and 2 below. To compensate for this, the F-117 needed extra large wings, 72 square meters. That's a huge wing area for such a lightweight aircraft. For comparison, the F-15 Eagle was designed for agility with a low wing loading. Yet the F-15 had smaller wings and a higher maximum takeoff weight than the F-117. The Eagle's more efficient wing design generated more lift with less surface area. Stealth design forced engineers to make other compromises too. The HAB-Blue test plane originally had a platypus tail extension that acted as a flight control surface. If the plane's angle of attack, that is, how much the nose pointed upward, went over 13 degrees, the tail would automatically move downward. But this system malfunctioned just 1 meter above the runway during a test flight. The plane slammed into the ground, bent its landing gear, and forced the pilot to eject. After that disaster, the platypus tail was removed from the final F-117 design. Another issue came from the way the plane was controlled. Unlike normal fighter jets with vertical tails, the F-117 had V-shaped tail fins that could move in different ways. If the fins moved opposite each other, they helped the plane turn. If they moved together, they controlled the nose's up and down movement. However, during steep climbs, the plane's fuselage blocked airflow to these fins, making them less effective. Engineers had to make adjustments to improve stability. The F-117's long-range missions added another challenge. To reach Saudi Arabia for Operation Desert Storm, these stealth jets had to fly for 15 hours and refuel 7 times mid-air. Their refueling system was built into the top of the fuselage and could rotate into position. But because the F-117 had poor low-speed handling, it wasn't suited for aircraft carriers. Lockheed once proposed a carrier-based version, the F-17N, which would have included a tailhook and bigger wings for better control. However, this idea never took off. Despite its quirks, the F-117 performed incredibly well in combat. During Desert Storm, 36 of these stealth jets operated from Saudi Arabia, hitting high-value targets deep in enemy airspace. On the first night alone, they struck 26 critical sites, including enemy air defense systems. Normally, such missions would require bombers, fighter escorts, electronic jammers, and refueling tankers, all at a huge cost. But the F-117 did the job with just a few refuelers for support. However, the Air Force knew that stealth wouldn't remain unbeatable forever. Once enemies become aware of stealth technology, they develop new ways to detect and counter it. The golden age of radar invisibility was destined to be short-lived, pushing military aviation into a new era of stealth evolution. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.